This is the complementary video to our bachelor thesis, End-to-End Deep Reinforcement Learning for Autonomous Racing Dynamics. This video only explains the basics. For further explanations, please read the thesis. The authors of this thesis are members of the Zurich UAS racing team. We compete in the electric vehicles category in the Formula Student Competition. We have used proximal policy optimization paired with a YOLO V8 network to train a reinforcement learning agent to learn racing dynamics. The agent was trained in Carla, an open source simulator for autonomous driving research based on Unreal Engine, which we modified to be able to simulate the 2024 Zur vehicle. We begin by showing the training of the acceleration event. The goal is to accelerate as hard as possible and reach the finish line fastest. The agent is currently in its exploration phase, which is why it crashes very early. The agent takes certain sensors, namely the accelerometer, the cone positions, as well as depth, and outputs values that are directly mapped to driving actions. It is important to note that the agent cannot access unrealistic variables like the center of the track or similar. This is what the agent sees during the acceleration race. We evaluated the fully trained agent on a track it has never seen before. As you can see, the agent completes the course with ease. In this discipline, the agent needs to stop after passing the finish line marked with 4 large orange cones. Here is the agent's point of view. In this video, a few cones have been moved to simulate inconsistencies. As you can see, the agent confidently handles those edge cases. The skid pad event determines the cornering capabilities of the car. In the training phase, you can see the agent driving around the course, occasionally crashing. Note that this footage is in the later stages of training. Up to 20 agents are trained simultaneously. The agents are spawned on waypoints to diversify the training samples to the whole track. Evaluating the skid pad agent, we noticed that the agent seems to attempt to drive too quickly. It starts to drift and loses control, which can be attributed to the reward function design. The agent also needs to decide on 3 different options in the center junction of the race: driving to the left, to the right, or going straight. We believe that this decision is hard for the network, as the options are very different even though the perception of the agent is similar. We arrive at the hardest of disciplines, the track drive event. Here the course is not known to the competitors beforehand. A single race consists of 10 laps around a longer track. As you can see, there are a variety of tracks with hairpins, straights, and bends. Each of these tracks was handcrafted, as a real course tends to not have perfect cone placement as well. and once again the agent's view of the track drive event. Sometimes other parts of the track are in the direct perception of the vehicle. This footage is in the later stages of training. As you can see, the agent navigates the course quite proficiently, but occasionally drives really slow or crashes. Here we are evaluating the fully trained track drive agent. You can see the agent crashing as well as finishing most of the course. This footage is close to the actual speed of the agent. The view explains why the agent seems to be sliding a lot. Some footage in this video is sped up. Here you can see the actual training speed on a desktop computer with a Ryzen 7 5700X and a GeForce RTX 3070 Ti. To train an agent from scratch on the track drive discipline, about 7 days of compute power is needed.